The sky over eastern Australia was a muted grey, low clouds spilling across the horizon like molten iron. The hum of turbines cut through the cockpit, steady, measured, almost hypnotic. Below, the patchwork of farmland and forests passed in muted tones, a silent witness to the approaching flight. Flight AIA 320 was on its routine approach, an Airbus A320 carrying 146 souls. In the cockpit, screens glowed with digital precision, altitudes, headings, speeds, all in perfect order. The crew worked in practiced rhythm, scanning instruments, cross-checking procedures. Outside, rain began to streak the windscreen, each droplet a subtle, persistent reminder of the environment pressing against them. Seconds stretched. The autopilot held the aircraft firmly on its glide path, yet subtle cues began to appear. An altitude slightly off, minor fluctuations in airspeed. The terrain below was unforgiving, ridges and valleys hidden beneath the gray blanket. The automated systems remained silent, untroubled, but the interplay of human and machine was about to be tested. There was no sudden alarm, no flash of catastrophe, only the quiet compression of time, the precise and methodical culmination of systems, decisions, and environment converging on a single point in space and fate. In these minutes, the story of AIA Flight 320 would unfold, a story of machines, humans, and circumstance intersecting in a way that would reshape aviation safety. Australian International Airlines had built a reputation for reliable service along the eastern and northern corridors of Australia. Established in the mid-1980s, the airline operated a modern fleet dominated by Airbus A320s, valued for their efficiency, fly-by-wire precision, and standardized cockpit environment. By 2000, the A320 was a common sight in the region, but routine familiarity could mask latent risk. Flight 320 was scheduled from Sydney to a regional airport known for its challenging approach. The airfield sat near low-lying ridges and undulating terrain, often shrouded in mist and sudden rain squalls. Pilots were trained extensively for the area, but real-world conditions could shift rapidly, testing even experienced crews. The A320 itself was a workhorse of modern aviation. Its fly-by-wire system, a digital interface between pilot inputs and control surfaces, allowed precise handling and automated protections against stall and overspeed. Pilots relied on it, but also needed constant awareness of the aircraft's mode. Automatic corrections could mask subtle deviations if not monitored. The cockpit environment was designed for vigilance, dual displays, multiple alerts, and redundancy across every critical system. Yet human factors, fatigue, expectation, and environmental stress, remained as influential as any system. The flight crew for this leg was experienced. The captain had accumulated over 12,000 flight hours, with substantial time on the A320. The first officer, while younger, was highly competent, recently completing advanced simulator training on approaches in complex terrain. Together, they represented the standard of operational proficiency. But in aviation, proficiency is tested not in normal flight, but at the edge of known conditions. Operational culture emphasized safety and procedural compliance, but small deviations, often imperceptible, could compound under pressure. Weather forecasts suggested scattered rain showers, low cloud layers, and variable wind near the destination. The aircraft systems would provide guidance, but decision-making ultimately remained human. As Flight 320 departed Sydney, routine procedures and pre-flight checks passed without incident. But the surrounding environment, the complex terrain, capricious weather, and precise demands of the A320 would converge in the next hour. What appeared to be an ordinary approach was setting the stage for a sequence of events that would demand a forensic reconstruction. The Airbus A320's design was as much about automation as it was about pilot interaction. Fly-by-wire technology replaced traditional mechanical linkages with digital commands, interpreted by flight control computers. The system offered protections, preventing stalls, limiting bank angles, and automatically adjusting for minor deviations. Yet this reliance on automation required constant monitoring. A small misread, a delayed reaction, or a misunderstood mode could magnify minor errors into critical hazards. The cockpit of Flight 320 reflected the intersection of precision and pressure. The captain, methodical and experienced, relied on procedural rigor. The first officer brought recent simulator training on approaches in complex terrain, sharp but still developing intuition under operational stress. Both pilots maintained standard operating procedures, but subtle cues, slightly delayed checklist execution, minor altitude deviations, introduced small cracks in situational awareness. In aviation, these cracks rarely announce themselves loudly. They accumulate silently. Weather added a dynamic, uncontrollable layer. Rain fell intermittently. Low clouds obscured visual references, and light winds shifted unpredictably near the ridges surrounding the destination airport. Such conditions demanded careful coordination between instrument guidance and human judgment. Instrument landing system readings, altimeter cross-checks, and approach charts were all essential, yet the environment required vigilance beyond standard procedures. From the system's perspective, the A320 provided multiple alerts, altitude deviation warnings, terrain proximity indicators, and autopilot status updates. Each alert carried weight, but a complex cockpit environment can produce alert saturation, where multiple minor warnings compete for attention. Pilots must interpret, prioritize, and act with clarity. On Flight 320, subtle deviations went unnoticed, compounded by environmental pressures and automated corrections that masked minor misalignments. The interplay of aircraft, crew, and environment created a fragile equilibrium. The aircraft executed automated adjustments flawlessly. The crew followed procedure. Yet nature and technology have a common trait. They tolerate minor lapses until they converge at a critical moment. In this balance, small misalignments, slight altitude variances, micro-adjustments in heading, brief lapses in cross-checks would cascade toward an irreversible outcome. Every angle, mechanical, human, environmental, was functioning within limits. And yet, limits are not guarantees. In aviation, the most controlled systems demand the most disciplined oversight. Flight 320 systems, crew, and context were about to collide with those limits in real time. As Flight 320 neared the regional airport, the landscape became less forgiving. Low ridges rose subtly through the cloud layer, invisible until mere seconds away. The autopilot maintained the programmed glide path, yet a small drift in altitude went unnoticed. Less than 100 feet, imperceptible in the rhythm of automated flight. Inside the cockpit, instruments displayed nominal readings. The Terrain Awareness and Warning System, TAWS, remained silent until the aircraft crossed a critical threshold. At that moment, the first alert sounded, a chime, a caution, a reminder of the proximity to the ground. Reaction was immediate but constrained by milliseconds. The captain initiated a climb, the first officer cross-checking altitudes, but the aircraft's rate of descent and terrain alignment left little margin. The last moments were a sequence of precise, mechanical responses, throttle adjustments, pitch changes, automated stabilizations. There was no panic, only rapid, disciplined effort. Yet nature and physics offered no concessions. The aircraft's proximity to the rising ridge compressed decision time. Every system functioned, every procedure executed, yet the combination of slight altitude misalignment, reduced visibility, and environmental pressure created a convergence the crew could not fully counteract. Seconds felt like minutes. The last TAWS alert sounded, Now a warning. The flight deck was awash in red indicators. Autopilot disengaged. Manual input required. Hands moved over throttles and side sticks. Eyes scanning instruments. Yet the aircraft remained on a trajectory dictated by prior deviations. The sequence ended with the aircraft contacting terrain at high speed. There was no explosion, no dramatic fireball, only the silence of finality, the abrupt end to a chain of interactions between human, machine, and environment. In aviation analysis, this is where lessons are extracted. The accumulation of small errors, the masking effect of automation, and the unforgiving nature of real-world conditions. Flight 320's final moments were methodical in their inevitability. Respectful reconstruction allows investigators and the public to understand the failure chain without sensationalizing the loss of life. Every action, every reading, every procedural choice contributed to an outcome that was preventable, but only in hindsight. In the hours following the accident, aviation authorities arrived on site. The scene was quiet, austere, a stark contrast to the complexity of the events that had unfolded minutes before. Black boxes were recovered intact. The cockpit voice recorder captured procedural dialogue, alert chimes, and the rhythm of the crew's efforts. The flight data recorder chronicled every control input, altitude change, and system response. Investigators began the painstaking process of reconstructing Flight 320's final moments. Data revealed a chain of minor deviations, slight altitude misalignments, small heading corrections, and delayed reactions to automated system cues. No single failure caused the accident. Instead, a combination of environmental pressures, minor human errors, and subtle automation masking led to controlled flight into terrain. Weather records corroborated the cockpit reports. Intermittent rain, low cloud, and gusting winds near ridges. Terrain maps confirmed that visual references would have been severely limited until the aircraft was dangerously close to the ground. Investigators noted the crew's disciplined adherence to procedures, underscoring the challenge of relying on human vigilance within highly automated systems. The report emphasized the critical role of automation understanding and situational awareness. Alerts were functioning correctly, but interpretation under stress proved insufficient to avert tragedy. Training protocols were reevaluated, highlighting the importance of reinforcing manual monitoring, early alert response, and scenario-based simulations for complex approaches. The airline, regulators, and Airbus worked collaboratively to implement changes. Approach procedures were refined, cockpit alert protocols were clarified, and additional simulator exercises were mandated. Safety culture evolved, not from fault-finding, but from understanding the subtle interplay of machine, human, and environment. Flight 320 became a reference case in international aviation circles for CFIT risk, automation reliance, and terrain awareness. In aviation, the aftermath of an accident is measured not in spectacle but in the precision of lessons learned. Flight 320's legacy is codified in procedural manuals, simulator exercises, and regulatory guidance, a somber reminder that safety is cumulative, not absolute. Flight 320's story does not end with the accident itself. It continues in the procedures, training, and technological refinements that followed. Aviation is a discipline where every loss reshapes the future. Every failure teaches the limits of human and machine interaction. Following the investigation, airlines and regulatory authorities emphasized scenario-based training for complex approaches, particularly in low visibility and mountainous terrain. Simulator programs incorporated CFIT scenarios, emphasizing rapid alert recognition and coordinated crew response. Manual monitoring of automated systems became a renewed focus, reinforcing the balance between trust in technology and human vigilance. Airbus and other manufacturers responded with refinements in cockpit alert logic and interface design. Terrain awareness systems were adjusted to provide earlier, more intuitive warnings, reducing the risk of late detection in high-pressure situations. Procedures for cross-checking autopilot modes and altitude adherence were strengthened, acknowledging that even highly automated aircraft depend on continuous human oversight. The legacy of Flight 320 is quiet, yet profound. It is present in the charts pilots study, in the checklist meticulously followed, and in the simulators that recreate high-risk conditions without consequence. Safety is cumulative, built not on dramatic revelations, but on understanding patterns, anticipating failure chains, and instilling disciplined response. For those who study aviation accidents, Flight 320 serves as a measured reminder: no technology, no matter how sophisticated, replaces awareness, judgment, and procedural rigor. Its lessons ripple outward, guiding pilots, engineers, and regulators alike. In this way, the lives lost become catalysts for enduring safety, ensuring that aviation continues to evolve methodically, intelligently, and responsibly. The silence in the skies over Eastern Australia remains unchanged.
Agreed.
Yet the lessons carved into procedure and practice endure. Flight 320 exists now not only in memory but in every safe approach, every alert correctly interpreted, and every margin preserved between human decision and environmental challenge.